Recording. Share my screen. Come over here. Okay, so welcome back to post-fall break data mining. There's two handouts for today. There's copies, physical copies up front if you're into physical copies. And if you want the electronic versions, where you can find them is under the 04 folder. And then the notes dash bottou is a notes file. And then there's a this file right here, which is going to act as sort of a textbook for us. Okay, let's focus, bring it together. So yeah, again, two PDF files, this one right here, this one right here. This one is the notes, similar form to the different notes that we've had before. And then this one right here is what's going to act as our textbook for this section. And both of these two things together is the last piece of material that we'll have for the next midterm exam. I think probably won't quite finish it all today. We still have a little bit of leftover notes to get through today. And then we'll start on this, probably finish with this on Monday next week. And then the exam tentatively the end of next week. Besides the exam coming up, you also have the programming due sort of nominally yesterday, but you have the 2 days with the extension. That's the IPython notebook thing, playing around with different VC dimension stuff. Any high-level questions about that? Yeah. Okay, go for it.
Like question 3.2 is like we ask you approximation error less than 1% or 1%. So like no matter what value that you're like putting, it's not quite there.
Yeah, so in terms of like how is grading going to work for the assignment, if you submit something and there's something like remotely reasonable in any of the questions, then you'll get full credit on it. If like for the problems that are specifically about like get a certain error on the problem, if after a bunch of fiddling around with it you can't actually quite get that error, then that's fine. Yeah, I guess, yeah, so the main point of it's not to like bang your head against the wall trying to get certain errors, but just to start getting a sense of like that the sort of theorems that we've been talking about, they are actually somehow playing out in the real world.
Like 3.2 asks for an approximation error less than 1%. But like even if you go really far out, like I tried P for 40, it took like hours to run, and it still was like asymptotically like 91%. Like out of standard error.
So okay, yeah. So the key here is difference between generalization error and the out of sample error. That the generalization error, the way the book defines it, is the difference between the out of sample and the in sample error. So if your out of sample error is not going down to 1%, then that would be expected. But you should be able to make the generalization error go down arbitrarily small with sufficient number of data points. I don't have the problem easily pull upable, so I can't verify exactly, but yeah, it's the difference between the generalization error. Anytime you see that, think difference between the in sample, out of sample errors. Is that sort of clarifying that, Karen? Or
I think on the question it asks for approximation error, which is that's test error, right? There's approximation error.
Yeah.
It says, it talks about, it's like on the question it says like we want to find like or if the hypothesis is realized by the data set, that means there exists like an approximation error such that like approximation error of 0 or such that
Right.
E out is equal to 0, and then it asks for what's the approximation error, what degree polynomial gets approximation error of less than 1%. So I think that was referring to E out as well, and not the generalization there.
Okay, yes, yeah. So then the approximation error is the it would be helpful if I could pull up the IPython notebook, but I think that'll be like a long process, so I'm not going to do that.
So basically, I was saying that as the lowest testing ever we could get, and that takes an hour to run. Never guessed it would be longer.
Yeah, so one of the things that you can control in the data sets that you're generating is the amount of noise in the data. And the amount of noise, if there's a high noise or if there's any noise, then the approximation error is going to be non-zero. That no matter what hypothesis class you select, you can't drive the out of sample error to 0 if there's fundamentally noise in the problem. And so if if in the limit as the number of the degree of the polynomial goes to infinity, whatever that approaches, that is the sometimes called the Bayes error, or the true error of the problem, the amount of noise inherent in the problem. And so if it's asking about the getting the approximation error less than 1%, then that means that your final error is within 1% of when the limit as the number of polynomials grows to infinity, what that error is. Good questions. I think follow-on questions related to that should happen after class. Any other questions about the assignment not related to that particular problem? Okay, maybe one last sort of announcement-ish thing is that I probably have more than 100 emails still sitting in my inbox. I didn't look at any of them while I was traveling. And so if you've sent me emails, I apologize I haven't responded yet. Sometime over the next day or two, I'll get through them all. But feel free to talk to me after class if there's something you'd like to talk about. So getting into the technical stuff, we're gonna start with a review of what we were talking about last time, finish up this set of notes on linear models, and then get into the new set of notes for today. And so big picture, we've been talking about all the statistical properties of our different hypothesis classes and learning algorithms. And then, and that was building up to this idea of VC dimension that we can use to control what our generalization error is going to be. And then last time we started talking about the computational properties. And we talked about that if you have a finite hypothesis class, it's easy to find the exact optimum of your minimization problem like this, sometimes called the empirical risk minimizer. But the finite hypothesis classes, the whole point of introducing the VC dimension stuff is so that we can deal with infinite hypothesis classes. And so now we're introducing optimization strategies for dealing with these infinite hypothesis classes. How do we actually efficiently find one of these hypotheses in the real world? And we introduced a bunch of new notation that was somehow like generalizations of the notation from the previous chapters. One of the main things we talked about was this square loss. There it is defined right here on equation 6. This is the only loss function that has a closed form solution. So closed form solution meant that we could do all this calculus here to find like an actual formula for the optimal solution. And again, the squared loss is the only loss that has that property. Squared loss is in particular used for regression problems, but the focus of this class and the focus of the VC dimension has been on binary classification problems. And with the binary loss, the 0-1 loss, we said that that's intractable to compute, that it's this NP-hard thing. And so although we don't know for sure, we have no proof that the runtimes are exponential, we have really good reason to believe that the runtimes are probably going to be exponential. And so we've started talking about how do we get around that problem. We introduced this idea of a surrogate loss function. And a surrogate loss function was a loss that somehow upper bounded the 0-1 loss. And we've been talking about this graph right here. This red line right here, this sort of block shape, that was the 0-1 loss. The x-axis here, this is important. The x-axis right here is this new z variable, where z is, I'll go ahead and write it out rather than going someplace else. But this z variable was defined to be the y w star or w transpose x, like that. That's what z is equal to. And so this is going to be a scalar here, and so the 0-1 loss is what we're applying to this scalar here to get this red line. This Q function up here is what we're actually plotting, that all these classification losses are somehow written in terms of this y w transpose x, and so we just plot them with the x-axis being this value right here. The intuition of this z value is on a plot like this, where we're plotting the data points in our feature space, where the pluses are the positive data points, the negatives are the negative data points, and this green line right here is a linear separating hyperplane. So an example of running the perceptron algorithm, the PLA algorithm. The z value is really like the way you should be thinking about it is as the sort of like this margin in terms of how far away is this this hyperplane from the data point that we're looking at. And yeah, so we plotted this 0-1 loss. That's the one that we are ideally would be interested in, but we can't compute that. It's computationally intractable. So we wanted to talk about surrogate loss functions, things that we can compute. And a surrogate loss function is any loss function that upper bounds the 0-1 loss. We've taken a look at 3 possible examples of surrogate loss functions so far, the exponential loss in blue. This one is a surrogate loss function because it is everywhere greater than or equal to the 0-1 loss. Similarly, the logistic loss, also a surrogate loss function. But we talked about this smooth 0-1 loss is not a surrogate loss function because there are portions that are below the 0-1 loss. So the surrogate is the first property of loss functions that we were talking about. The second property is the convexity of loss functions. And here, this blue line, the exponential loss, convex because anywhere you connect 2 points on the line, the connection line, this dotted line right here, is always above the actual blue line itself. Logistic loss also convex, but this smooth loss, smooth 0-1 loss, not convex because we could find 2 points where the line between them lies below the loss function itself. An intuitive way of thinking about convexity is that if your loss function somehow ever curves downward, then it's non-convex. If the loss function is only curving upward, so it only has a positive second derivative, then it's going to be convex. Any questions up to this point about the things that we've talked about or where we're going? Okay, so I have a bunch of examples up here listed of different loss functions. Again, we've talked about the exponential loss, we've talked about the logistic loss and the smooth 0-1 loss. These other ones we haven't talked about, but you're responsible for them for the midterm. And so you'll want to understand whether they're surrogates or whether they're convex. All of these, so far, all of our examples of surrogate losses and convex. If it's been surrogate, it's also been convex, and if it's convex, it's also been surrogate, but that's not in general true. And so some of these other examples will show you that that's not in general true. The last property that we were interested in is robustness, and we haven't, where we left off was talking about robustness. We haven't talked about that yet. So what is the idea of a robust loss function? Well, for our previous definitions for surrogate losses and for convex losses, we had like formal definitions. We could say that something is a surrogate or is convex, or whether it's not. For our robustness, we're not, I have a very informally stated definition right here. And that'll be good enough for our purposes. We're not going to get super formal about robustness. But the idea is that the closer a loss function is to the 0-1 loss, the more robust it is to outliers. And so down here, this X function it's a surrogate loss, it's convex, but it's very different than the 0-1 loss. The logistic loss is more similar to the 0-1 loss than the exponential loss. So we'll say that the logistic loss is more robust than the exponential loss. And always, when we're talking about robustness, it'll just be a matter of looking at the graph and saying, does it look more like the 0-1 loss or less like the 0-1 loss? And it'll always be pretty obvious about which one's more similar. For all of these loss functions, actually, I ordered them in terms of robustness, where up here is less robust, and down at the bottom is more robust. And it also turns out that the logistic loss is basically like as close as possible to the 0-1 loss as you can get and still be convex. Proving that somehow requires a lot of formality about like exactly what does it mean to be robust, and gets into a bunch of real analysis. But here we'll say that this one is like medium robust. And it's essentially as close to the 0-1 loss as you can get with still being convex. The reason we want convexity, again, we mentioned this at a high level, is that you'll be able to optimize efficiently something that's convex. And so one of the reasons why logistic regression is somehow is so often the standard like go-to algorithm is because we can efficiently optimize it. It's convex and it's as close to the 0-1 loss basically as possible. There are other classification algorithms based on the squared loss or the exponential loss. They're also surrogates, they're also convex, so they can be efficiently optimized, but they're not as close to the 0-1 loss, so they're just not as useful in practice as the logistic loss is right here. Any questions about that? Yes, no. Question is a straight line convex? And the answer is yes. So it doesn't have to be strictly above the separating line. It just has to be, I guess, not below the line. So this hinge loss right here, let's go ahead and think about that. I don't have another good color, so we'll use blue for the hinge loss. The hinge loss looks basically just like the logistic loss, that it is a straight line passing through the dot right here, intersects the origin, and then this max at 0 makes it a straight line over here. So the hinge loss, it is a surrogate. Yes, it is convex. Yes. And again, it's extremely close to the logistic loss and basically as close to the 0-1 loss as you can get, with still being both a surrogate and convex. So also say that it's mediumly robust. Sometimes, so the learning model that uses the hinge loss is sometimes called the SVM, or it's always called the SVM. If you looked on scikit-learn and you wanted to use the hinge loss, you'd be using the support vector machine is what SVM stands for. And then the logistic loss here is logistic regression. But logistic regression and the SVM basically always give you the same results because their loss functions are so close to each other. Good question. Any other questions so far? Okay. A little bit more intuition about these loss functions. Down here in this blank section, I'm going to draw some more plots. And these plots, so up here, notice that on the x-axis, I have this z value, which is y w transpose x. On these plots, I'm going to draw the x-axis as the w. So this is the weight vector. And again, the weight vector in general can be multidimensional. So this is just a one-dimensional projection of the weight vector. And then the y-axis is going to be the loss function, not of a single sample. So up here, these are the loss functions on a single sample, but the y value here is going to be the full empirical loss of the E sub n. But then the E sub n applied with some of the different loss functions. One of the reasons this topic is really hard is that there's a bunch of very classic graphs that, so we've seen some of them, we're about to see some more. And these classic graphs have very subtle differences about what is the X and the Y axis. And like if it takes you literally dozens of hours of staring at these graphs before they click, then that's totally okay because that's how long it takes most people. These just understanding all the different subtleties of these graphs is complicated and takes a long time. But here, so again, this is the training error, the in-sample error on many data points. And if we plot this for the 0-1 loss, then what this looks like is a bunch of sort of square, jaggedy things like this. All these lines are meant to be vertical up and down. So it doesn't actually like cross the origin sort of like that, it is a true function. And the intuition about why the 0-1 loss is hard to optimize is because no matter like where you are on this particular graph, like let's say your current guess of W is right here, there's no way for us to know just looking at this particular point, should I go left or should I go right? And even if we somehow like manage to get to an optimal, a local optimum, there's no way for us to know whether that optimum is global or not global without doing lots of extra computations, basically trying every possible location. And so that's sort of like, I mean, this is just an ugly looking graph. It makes sense that it would be hard to find the whatever the global minimum of a graph like this is. The smooth 0-1 loss has a similar shape. So this is the smooth 0-1. It's going to have a similar shape, but it'll be like more smooth. But the key thing again is that with this, because it's not convex, just because we're at a local minimum doesn't mean we're at a global minimum. And so if we're at this point right here, there's no way for us to know whether we're at a global minimum or not unless we try a whole bunch more values. And so the smooth 0-1 loss is also not efficient to optimize. And it's the lack of convexity which gives us these weird shapes. The logistic loss The logistic loss, because it's convex, when we consider all the data points together, it's going to remain convex, and it's going to give us some like smoothish looking thing like this. One way to think about convex functions is that they're sort of like generalizations of quadratic functions, that no matter like how you draw it at some point is just going to look like very quadratic-ish. So I've tried to draw some like clear bends in here that are not, so that it's not like exactly a quadratic function, but all convex functions, if you squint and just blur your eyes, they're going to look fairly quadratic. And then the key idea of the logistic loss or any of these convex loss functions is that once you find a local minimum, it's guaranteed to be a global minimum. And so that's why the convexity property is good. It's convexity that gives us this property. And it happens to be true for the logistic loss. And again, the logistic loss is the most robust of those loss functions that has this property. Are there any questions about these three graphs? Sophia. First.
Do you know over the smooth 0, 1 again?
So the question is, why is the smooth 0, 1 loss like it is, and why is this point here? The smooth 0, 1 loss is essentially the most robust of our possible different loss functions, that this really closely emulates the 0, 1 loss. And actually, I didn't mention this before, but it's parameterized by this alpha value right here. And in the limit as alpha goes to infinity, the smooth 0, 1 loss approaches the 0, 1 loss exactly. So the smooth 0, 1 equals the 0, 1 loss. And so what this implies is that it is like the most robust loss function possible, because it can be exactly equal to the 0, 1 loss. But that also implies that the graph of the 0, 1 loss, smooth 0, 1 loss, is going to be very similar to the 0, 1 loss. So it's going to have all these sort of like jagged up and downs. I've drawn it with like smoothing out the corners because that's why it's smooth instead of exactly the 0, 1 loss. But because it's so robust, it is not convex. And so we haven't talked about how you might find one of these points yet. But if you did find one of these points, if you did somehow find a minimum of this function, like this point right here, this is a local minimum. But even though it's a local minimum, it is not a global minimum. It would be better to have this point down here. But there's just looking at like where we're at, there's no way for us to know whether we've hit the global minimum or not. In order to know if you've hit the global minimum, again, we don't have a proof of this, but the intuition is that you basically have to try every possible point, find all the possible minimums, and there's going to be an exponential number of them. And so you'll have an exponential runtime to find the global minimum. I don't know, did that answer your question somewhere? No, so yeah, there's many, many local minima. Yeah, so the question is that, so in some sense, what I've stated here is a little bit informal. And in particular, if we're only looking at like a subset of the W space. So what I'm going to draw next in blue is part of the answer to this question and totally unrelated to everything else on this graph. But if we're only looking at this, say, blue interval right here, then now the minimum of this point is right here and not over here. It turns out, though, that on this subset, no matter, as long as your constrained region is also convex, then any local minimum in this region is also going to be a global minimum constrained to this region. And it also turns out that we don't in practice use constraints when we're solving logistic regression problems. We consider all possible W values. So it's any local minimum anywhere is going to be the overall global minimum of the function. The other part of the question is that do these like, I don't know, kink sort of parts of the graph somehow cause problems? And the answer is that essentially no, because if we're, say, at this kink right here, then we know we're not at a local minimum because we could still be going to the left and decrease the value further. So just because there's kinks in the graph doesn't affect this property about the local versus global minimum. Does that answer your question? This is a super high level discussion of all of these concepts. And at this point, I think it's useful to take a step back and think about some of the, like, I guess, the strengths and weaknesses of the textbook and why I chose this textbook for our class. So again, this textbook comes from Caltech. It's their, they call their class Learning from Data instead of data mining. But it's what they use. They use a quarter system instead of a semester system. So the textbook's really designed for a quarter system. And they also have a second class that goes along with it that's just on these optimization problems. So the textbook is intended to sort of be supplemented somehow with a different discussion of optimization. And so that's what we're going to do with this other paper. This is going to be our sort of supplement to the textbook to yeah, I guess emulate that what they're doing at Caltech. The reason I chose this textbook is because it's really the only textbook that has, I think, an approachable introduction to the VC dimension stuff for at like an undergraduate level, not at a master's or PhD level. So that's why we chose it. But then we'll have to supplement our discussions about optimization a little bit. If we come over to the textbook, you can see that it has these sorts of pictures that we were just looking at. And again, the y-axis or the x-axis here, it's not explicit, but that's the weights W. They made it explicit down here. And so here's our convex picture. Here's our non-convex picture. They give us a little bit of intuitive description of this gradient descent algorithm. The basic idea is that no matter where you start at, you just keep going downhill until you get to a local minimum. And so the problem is going to be that you'll get stuck at a local minimum with a graph like this. But if you reach a local minimum with a graph like this, then you'll be okay. So that's why we want things to be convex. But our next paper is going to make that all a little bit more formal for us and more practical. So any questions before we get started with this next last set of material before the midterm? Okay, we're going to go over this this paper a little bit differently than we've done for the textbook. I'm going to we're going to directly use this paper as our set of notes, and I'll be annotating stuff inside this paper. It's going to be essentially impossible on the midterm to do well in this section without reading this paper. And so the main purpose of our discussion in class is going to give you the, I guess, the background to be able to read this paper and answer good questions about this paper. There's a number of reasons why we're looking at this paper in particular. So first of all, this guy, bottou, is very famous. I like to look at pictures of all the famous people we talk about. So let's go over here. Here's a picture of him right here. He, at the time that he wrote this, he worked at NEC Labs, but in 2015, he switched over to Facebook, and he's been working at Facebook since then. The other, so we talked about the random projections technique introduced in 2007, earned a Test of Time award at the NeurIPS conference. This paper actually that we're reading right now, this one that we're looking at, also earned the Test of Time award at NeurIPS. This was originally published also in 2007, and this was the 2018 award that he was awarded. He shared it with this other guy, Olivier Busquet, who currently works at Google. And yeah, so they earned this award. They got this award because they sort of the first works that talked about efficient optimization algorithms for very large scale machine learning problems. And so that's what we're going to be learning about reading it, is these optimization algorithms for large scale machine learning. And after we're done with this, we'll be like, you'll know everything up to 2007, what was state of the art in machine learning. And all that stuff still continues to be state of the art for many, many practical problems today. Another reason why we're looking at this paper or a paper outside the textbook is one of the goals of this class is to get you to be able to read papers on your own about machine learning or data mining. The field's changing so fast that no matter like what material we'll cover in the actual class here, 5 years from now, it's all going to be out of date. And so you're going to have to, in order to keep up, be able to read the material and understand what's going on. And so downside of using this paper, also an upside, is that the notation is totally different from that of the book. And so this very first part, what we're talking about is going to be how the notation matches or is different than the notation in the book. And as you're reading this, you'll have to be comfortable with using those two different notations. On the midterm exam, I'll always be clear about exactly which notation I'm using on any particular problem. But some of the questions will use the notation from the book, and some of the questions will use the notation from this paper right here. So let's get started. This section 2 is introducing at the beginning here all the different notations. The first thing is that, so we still have data points, X, Y. The X is our input, the Y is our output. But now this input X is not in bold. So that's a super minor thing, not in bold. And these Z's are like the full data point, the X, Y pair. So that's still the same. X equals X, Y, which is the same as the textbook. And our previous notes. We still have this loss function, L y hat comma y. That's the same as what we've seen before. This y hat again is going to be, well, actually, here's the spot where they do it. Well, this y hat is the predicted y value. Anytime you see a variable somehow wearing a hat, that hat means that it's been estimated from data somehow. So this y without a hat is the true y. The y wearing the hat is the estimated from data y. The first main difference they have is that this big bold F, that is our hypothesis class. So this paper says like F sub W in big F for a function in a set of functions, whereas the textbook says a little h inside of the fancy, big H for a hypothesis inside of a hypothesis class. And so the hypothesis and function are used interchangeably. And so they're using function in this paper, so they use F instead of H. We still have this this Q, again, this L right here, this this F sub W of X, that's equal to the Y hat. And again, the F is our hypothesis, our function. And so this is our estimated output on that particular X example right here. There's down here, every paper is always going to start with this sort of paragraph somehow introducing all their notation, and they're always going to somehow define what is their out of sample error and what is their in sample error. This thing on the left over here is the E out in the book, the out of sample error. And this thing on the right over here is the E sub in, the in sample error. And another sort of minor difference is here in the paper, they're using lowercase n's for the total number of data points. The textbook uses uppercase n. I've been intentionally using this term empirical risk a lot of the times when instead of the in-sample error, this empirical risk is just another equivalent name for the in-sample error. People use these terms interchangeably. Again, empirical is the in-sample, risk is the error. And they're using expected risk is what they call the out of sample error. And then they have this last sentence about statistical learning theory. So VC theory justifies minimizing this empirical risk instead of the expected risk when the chosen family F is sufficiently restrictive. And sufficiently restrictive, you're just supposed to know that that means that the VC dimension, dVC, is approximately equal to the number of data points that you have. And again, by our VC dimension theorem, the generalization error is bounded by the ratio of the VC dimension and the number of data points. So if those two things are approximately equal, then we're going to have a relatively small VC dimension. Any questions about any of that stuff notationally? The difference between the notations of the paper and the book? Okay, it's very easy to get lost in those definitions. So if you feel like you don't have questions now, but you feel lost in the future, that's a normal place to be. And just going back and forth between them a bunch will get you that more familiarity. Our discussion of, so there's going to be 4 different algorithms that we're going to be talking about, or that they introduce in this paper to solve these optimization problems. We're going to talk about all 4 of those algorithms at the beginning here algebraically. So today we'll probably only get to the algebraic discussion. And then after we're done talking about the algebraic stuff, then we'll get to the more geometric, interpretive, easier, maybe intuitively to understand part next week. But I think it's important, again, when these papers present things, they almost always present them in terms of the algebra, just because it's easier to write about. And so it's important to get this comfort, this familiarity with working with algebraic terms, even if you don't have a good geometric understanding of them. So we're going to start again without trying to get that geometric understanding, start with the algebra, and then hit the geometry next week. So our gradient descent algorithm, the very first algorithm that we're looking at, our goal is to minimize the empirical risk. So again, this right here, minimizing this term right here. And the idea is that we have this iterative procedure. We'll start with some W naught. We don't really care what it's going to be. And then we apply this rule over and over again in order to approximate this empirical risk right here. This term, the way to understand it this whole thing right over here is equal to the gradient of our empirical risk of that particular loss function. So it's called gradient descent because we are taking the gradient at each iteration right here. And again, our goal, so when they're saying their goal is to minimize the empirical risk up here in more formulaic terms, that's saying that our goal is to compute the arg min over f in fancy f of E sub n of f. Since this is the thing that we're minimizing, that's the thing that we're taking the gradient of over here. This gamma value right here, this is a scalar. And in the book they call it, or in the paper right here, they call it a gain. But gamma is a scalar. And it also has a bunch of other names. A common other name for it, the most popular one these days, is the learning rate of your algorithm. But everybody in the data mining machine learning world knows that learning rate is the same as the gain, is also called the step size. So it's this gamma value right here. It's somehow like what we're scaling our gradient by in order to do our step each time. Anytime we have one of these optimization algorithms, we've seen two examples so far, or we've seen many examples so far. We've seen the PLA and we've seen different optimizations for the that graph thing that we did at the beginning, PageRank. There's two questions that we always want to know. We want to know what is the runtime of each iteration, and we want to know how many iterations do we need. In order to know the runtime of this iteration here, we need to know a little bit more about this Q formula, or this Q function, which they don't talk about in this paper. They just assume that you're familiar with it. And so that's where we're going to switch over now to this set of notes here. And we'll talk a little bit more about our Q function, the important properties of it, and then we'll switch back to the paper. So for the logistic loss, which again we defined, and on the previous set of notes, the linear model notes, the logistic loss looks something like this. The Z again, y hat y, x transpose wy. And the first question here is, what is the gradient of the logistic loss? So in this class, I'm never going to force you to go do this calculus by hand. And instead, anytime there's a calculus sort of question, the matrixcalculus.org website is what we'll turn to. So I already have that open over here, matrixcalculus.org, and right here I've typed in the logistic loss for us. We're taking the gradient with respect to W. That's important. Every time we're taking these gradients, it's always with respect to the parameters. And so here is what the output looks like. I will copy that over here. So the gradient of W of Q of Z equals, and then so that's sometimes written Q prime of Z, the prime just indicating that we're taking the gradient with respect to W. We know that this is making what we're taking the gradient with explicit, but whenever it's not written, it's always with respect to the weights that we're taking the gradient. And that's equal to negative T naught divided by T naught Y divided by 1 plus T naught times X, where this T naught is equal to the X of negative Y W transpose X, like that. And again, not expecting you to be able to do this by hand. You can always just go to the matrixcalculus.org webpage, type in the formula, and get the results. And so I just copied down the results exactly right there. The important thing for us at this point is going to be the shape of all of these terms right here. So this T naught right here, what is the shape of this T naught variable? Is it a scalar or vector matrix? It's going to be a scalar. How do we know it's a scalar? Well, this W transpose X, W and X are both vectors. The inner product of the two vectors is going to be a scalar times Y is a scalar, and then exponent of that is just a scalar. So this is scalar and the real numbers. This thing up here at the top, all this stuff to the left is just scalars being multiplied together. So that whole thing's a scalar. And then this X over here is a vector. And so that'll be R to the D. The D is not explicitly discussed anywhere in this part of the notes, but the D is the dimension of all of our vectors. And so then my expectation is also that given something like this, you can work through what the runtime, calculating the runtime of something like this is going to be. And in this case, if you work through all that, then the runtime is going to be theta of D. We're just doing inner products and scalar multiplication here. So theta of D is going to be our runtime. Any questions about any of that? Okay, since we're already on this page, let's go ahead and do the second degree or the second derivative, the Hessian, often called the second derivative. And in this case, I'm not going to explicitly write out this. I'm not going to explicitly write that out. If you need it at some point, you know, you'll be able to go to the matrixcalculus.org and calculate it. And instead, what we'll look at, or what I'll just state, is that the shape of that is going to be R to the D by D, and the runtime is going to be theta of D squared. Those will be the things that will, the properties that we'll actually need of that. And you can verify that again, matrixcalculus.org. So we did both of these terms, both of these things explicitly in terms of the logistic regression loss right here. But the shapes and the runtimes are pretty much general for any type of loss function that you might consider. Okay, so now that we know what the shape of this thing is over here, we can start thinking about what is going to be the runtime of computing one iteration of gradient descent. We know that, again, this thing over here, the shape is R to the D. This thing over here is a scalar. So we have a scalar multiplication in different vector sums, and then a vector subtraction over here. And if you work all that out, the runtime is going to be theta of n times d. The n comes from this summation right here. There's n different things that we're summing together, and the d comes from the fact that they're d-dimensional vectors that we're working with. Any questions about that? Okay, the number of iterations that we need. So they talk about that right here. Rho is specifically the accuracy that we're trying to get to. So the rho value is going to be the difference between what we our WT plus 1 and the optimal of this minimization here. And rho is going to be O of log t, however many iterations that you've done. Sorry, log 1 over. The iterations to the number of iterations that you need, number of iterations for accuracy row is equal to the log of 1 over row, and that's big O of that. For all 4 of these, so yeah, this is the first algorithm that we've talked about for all 4 of them. We're going to talk about the different runtimes and the number of iterations that you need for each one. But this is all summarized in a table at the end. So I'm going to scroll down here in a second. This is table 2 on page 6. It has the runtime per iteration. This is all ignoring the dimensionality factor. The runtime per iteration ignoring the dimension. So whereas we wrote that it was in times d on the runtimes per iteration, they just put in here ignoring the dependence on d. And then the iterations to accuracy row is this log of 1 over row. It doesn't actually depend on d at all. Yeah, so what I wrote above is these 2 first things right here. The difference between gradient descent and the next algorithm is second order gradient descent, is that in the second order gradient descent, we've replaced gamma by this matrix right here. So the only difference between formula 2 and formula 3 is that we have a matrix right here. It's backwards. Gamma sub t is a matrix R to the d by d. And somehow gamma sub t should be approximately equal to the gradient with respect to w squared of our q function, and then the inverse of that. And that's what they're saying at when the cost is quadratic in the scaling matrix, gamma is exact. So gamma t approaches the inverse of the Hessian. Gamma t, this is the inverse of the Hessian matrix right here. When that is exactly equal to each other, that's an exact version of second order gradient descent. In general, so if we were to exactly compute this right here, exact runtime, this is going to be O of and d squared plus d cubed. The d cubed coming from the fact that we're doing an inverse operation right here. The nd squared coming from the fact that our E sub n, I guess this most correctly as E sub n right here. The E sub n having the 1 over n inside of it. And so this is the exact runtime. This is very large, and so usually this can be approximated. And there's lots of various ways of approximating it. We're not going to go into any of those details, but approximate versions are faster. We want to talk about the runtime of this equation right here and the number of iterations that we need. The runtime is, so again, this part is the same as above, but now we have a matrix multiplication going on right here. And so that'll be theta of n times d for this, n times d. And then we have a matrix vector multiplication, so plus d squared, like that. N times d plus d squared, the n times d for this term over here, the d squared for the matrix multiplication of gamma t times all of this. And this runtime right here, it doesn't take into consideration the runtime of computing gamma t. That's just assuming that we already have the gamma t computed for us somehow. And this over here, the typical runtimes of gamma t can be bigger than this runtime over here. So this runtime could be slower than this, but it's never going to be faster than this. The advantage of the second order algorithm is that the number of iterations that you'll need is going to be much smaller. So here it's not just the log of rho, but the log of rho. And so the number of iterations is going to be O of log 1 over rho, like that. And again, this value and this value are contained in that table 2, with the exception that table 2 doesn't consider the dependence on D that we have up here. So what we have so far is that there's somehow a trade-off between gradient descent and the second order gradient descent, where the second order version needs fewer iterations. It's the log of the log, but the runtime of each iteration is going to be bigger in terms of its dependence on D. Any questions about, yes?
Sorry, this number of iterations, that's log 1 over.
It's log 1 over rho, and that's also in this this table 2 right here, iterations to accuracy rho, log 1 over rho right here. Next two algorithms that we have are stochastic gradient descent and second order stochastic gradient descent. The idea of stochastic gradient descent, so this equation right here is exactly the same as the equation for gradient descent, except you'll notice there is no summation right here. No summation. And so the runtime is now faster, that there's no dependence on n right on here. We just have a single scalar vector multiplication. So the runtime is going to be theta of d. But then the downside is that the number of iterations that we'll need is going to be larger. And the number iterations will be O of 1 over rho. So we've taken away that logarithm. So it's very, very many iterations larger, but potentially much, much faster runtime. So it's somehow like a major trade-off here that we're doing, that we're making. Each one of our updates is going to be much, much less accurate. But the hope is that by making a lot of them, we'll get better results. And then scrolling way down here to equation 5, this is the second order stochastic gradient descent to SGD algorithm. And now this is just like our second order gradient descent algorithm, but there's no summation. No summation. So the run time per iteration, we have still have a vector matrix product right here. So that's going to be theta d squared. We've taken away the n times d term on our runtime, but we still have the matrix vector product to get theta d squared. But our number of iterations turns out is going to remain at O of 1 over rho. So here, if you compare second order gradient descent to first order gradient descent, the runtime per iteration of second order gradient descent is strictly slower, that it takes quadratic time in terms of the dimension instead of linear time. But the number of iterations is going to be exactly the same, O of 1 over rho. And so there's basically no situation where you want to use second order gradient descent. No situation where 2SGD faster than the SGD. Because again, it's still the same number of iterations, it's just more runtime per iteration. Any questions about those facts, those runtimes that we've copied down? Okay. This section 2.3 is something that you can basically skip over. It's examples related to various algorithms that were popular at the time. Just highlights are that the perceptron is just actually a concrete example, a specific example of SGD with a particular loss function. Here's the SVM. This is the hinge loss right here, if you remember that from the previous page. So the SVM and perceptron, concrete examples of these things. We'll talk about this section 3, I think, next time. But first, let's switch back over to our notes over here. And on the next page on the notes, there's this table 2. This is again just an exact replica of the table 2 from the paper. The table 2 from the paper doesn't talk about the d-dimensionality dependence. So let's just add that in to these terms right here. Gradient descent, we had d times n. To gradient descent, we had dn plus d squared. SGD was just d, to SGD was the d squared. So those are the runtimes that we just explicitly stated before. The number of iterations to a particular accuracy row does not depend in any way on the dimensions. So these things stay the same no matter what your dimension is. And then your total time to a particular accuracy is the number of iterations you have to do times the runtime per iteration. So what's written here is just this thing times this thing. In order to make this third line here depend on the dimension, you also have to copy down the d factor down here. So that's a dn d squared plus that. That's d, and that's d squared right there. And then, yeah, this last row right here is part of the section 3 of the paper. So we'll get to that next time, and also start talking about the intuition of these things. But at least at this point, what you can hopefully see is that there's going to be some trade-offs that we'll be making about whether you want more accuracy or less accuracy, about the number of samples that you have, about the number of dimensions that you have, and which one of these algorithms that you choose will depend on those factors. But you'll never want to choose second order stochastic gradient descent, because this thing is always going to be bigger than this thing right here, no matter what problem you're using. So it'll always be these 3 things that you have to pick from. If there's any questions that people have, we can talk about that after class, about this or about the homework assignment. But this is a good stopping point for us for today. Question is, when is the midterm? And the answer is that we'll finish all the material, probably next class section, and then it's tentatively scheduled for the end of next week. But if a quorum of people want it to be the following week, then after Halloween, this would be the scariest part of your Halloween, the midterm. I'm open to making it after Halloween if lots of people want that.